Greetings of the day, dear students. Today in this class or in this video, we are going to discuss about the parallel resonance. Right? Already we have completed the series resonance. Before watching this video, please complete the series resonance. Uh, in series resonance, if you have observed some basic summary, or I will just recollect for your sake, right, where the condition is the imaginary part of the impedance is made 0. The imaginary part of the impedance is made 0, right? And we got the resonant frequency as omega naught equal to 1 by root LC. Omega naught equal to 1 by root LC. What about bandwidth? It's the difference of the half power frequencies omega 2 minus omega 1, and the quality factor Q equals to omega naught by bandwidth. This is what we have seen in the series resonance. Coming to the parallel resonance, in this context, R, L and C are connected in parallel. Resistor, inductor and capacitor are connected in parallel. Now, uh, the impedance of the resistor R, and for inductor j omega L, and for capacitor it is 1 by j omega C. Just like in our series resonance, how we made the imaginary part of the impedance Z equal to 0, here also what we will do is imaginary part of admittance will be made 0. Very important. Which one is to be made 0, dear students? Imaginary part of admittance Y is to be made 0, right? If you recollect the basics of impedance and admittance calculations, right? For example, if three impedances Z1, Z2 and Z3, Z1, Z2 and Z3 are in series, what is the Z equivalent? It is simply Z1 plus Z2 plus Z3. Similarly, if three admittances are in parallel, Y1, Y2 and Y3. Now these are admittances Y1, Y2 and Y3 are in parallel. Then looking into the circuit, what is the Y equivalent? Your Y equivalent will be Y1 plus Y2 plus Y3. This basic is very important. The common mistake you may do is 1 by Y equivalent equal to 1 by Y R plus 1 by YL plus 1 by YC, but that is wrong. If impedances are in series, then we will add like this. But if admittances are in parallel, then Y equivalent equal to Y1 plus Y2 plus Y3. Of course, the impedances are in parallel. What we will do? 1 by Z equivalent equal to 1 by Z1 plus 1 by Z2 plus 1 by Z3. That is correct if impedances are in parallel. For example, if admittances are in series, Y1, Y2 and Y3 are in series, Y1, Y2 and Y3 are in series, then 1 by Y equivalent we have to take. 1 by Y equivalent equal to 1 by Y1 plus 1 by Y2 plus 1 by Y3. These four basics are very important. If you understand these basics, then this step you will not feel difficult, right? So Y equivalent equal to, but what is YR? 1 by R. YL admittance of inductor j omega L we are having 1 by j omega L, right? And for capacitor 1 divided by 1 by j omega C, right? Now if you take out j common, we will get 1 by r plus j of omega c minus 1 by omega l. This step is very important. Clear? I repeat again. Imaginary part of the admittance is to be made 0. Imaginary part of the admittance is to be made 0. At that point, at that condition, whatever the frequency is existing, that frequency is the resonant frequency or resonance frequency. Now observe omega c minus 1 by omega l equal to 0. Omega c equal to 1 by omega l. Omega square equal to 1 by LC. At that particular frequency, that is to be denoted with omega naught, resonant frequency. The frequency at which this condition is satisfied, that frequency is the resonant frequency omega naught. Omega naught equal to 1 by root LC, radians per second. And also we know that omega naught equal to 2 pi f. Therefore, f naught equal to omega naught by 2 pi. F naught equal to omega naught by 2 pi. We will get 1 by 2 pi root LC. Very important. 1 by 2 pi root LC. And the units are H. For omega naught, the units are radian per second. Radians per second. Clear? Out of this entire discussion, the important point is you please calculate the admittance if it is parallel circuit. If it is series circuit, you first calculate the impedance. And of course, you know the relation between Z and Y. Y admittance equal to reciprocal of the impedance 1 by Z. Clear? Y equal to 1 by Z. If you are not interested to find admittance, you do one thing. You find impedance for this one, and at last you take the inverse of the impedance. That is also okay. That is also okay, right? Yeah. Now let me see the other factors. What happened? Now this at resonance condition, this at the parallel, in the parallel LC combination acts like a open circuit. So during resonance condition, the circuit may look something like this. If a current is flowing like this, exactly at resonance, if you are having R, L and C combination is there, no? LC are in parallel only. This L and C are in parallel only. Now there will be a open circuit. The current will not flow through this path. Current I equal to 0 through this path. Here some current I will be flowing. This current IS comes up to here and it flows through resistor. The entire current flows through resistor LC. It acts like open circuit. The combination acts like open circuit. Exactly during resonance condition, the circuit behaves like this. That is the meaning. This is the current, applied current, some IS. Like this you have to understand. Now the entire current flows to the resistor. That is the meaning. Now what will be the voltage? Current Im into R. The current flowing through the resistor into impedance, resistor value. Right? Now IL value. It is simply the voltage across parallel combination divided by omega naught L. It will be quality factor times Im, and IC will be V by Z. Somewhere if you want, we know the basics. V equal to I into Z. If I want I, it is simply V divided by Z. That is what we have done here. For inductor, impedance is omega naught L. For capacitor, impedance is 1 by omega naught C. and this current will be quality factor times Im, right? Now what about quality factor Q? It is simply R by omega naught L, or R into omega naught C, R into omega naught C. That will be our quality factor Q. In the series resonance condition, we have clearly explained and derived, right, the condition for quality factor. If you recollect, quality factor Q indicates what? If you have already watched the series resonance, quality factor Q indicates the sharpness. See here, it indicates the sharpness of the resonance. Sharpness of the resonance. And for at this context, I have told you some three examples also. That is the reason I am asking you, before watching parallel resonance, please complete watching the series resonance. If this is one waveform and if this is the other waveform, this is having more sharpness. Sharpness of A is more. B curve is very flat. For this curve, if this is the maximum value at series resonance, if this is the resonance frequency omega naught, and half power frequency somewhere we will get here omega 1, and here omega 2, and this gap is nothing but the bandwidth. But for you observe, for the flat curve, if this is the maximum value, if at half power frequencies will be at Im by root 2 somewhere here, and this is omega 1 for this curve, and this is omega 2. If the curve is very flat, the bandwidth will be up to here. This is the bandwidth for curve B. So quality factor indicates the sharpness of the resonance. Sharpness of the resonance. That is what we have seen here. Or 2 pi times energy stored in the circuit divided by energy dissipated in the circuit. Omega naught L by R, or 1 by omega naught RC we got in the series resonance. Similarly, here quality factor Q equals to R by omega naught L, and it is also same as omega naught R times omega naught C, right? Now half power frequencies in the series resonance derivation, just simply replace R with 1 by R and L with 1 by C and C with 1 by L, right? Then we will obtain the equation for omega 1 and omega 2. If you want to find out the bandwidth, simply W2 minus W1, it is equal to the 1 by RC. And also we know that omega naught equal to 1 by root LC. Now the quality factor Q is given by omega naught by bandwidth. But omega naught by what is the bandwidth? 1 by RC. So it is same as omega naught into RC. This is also same as R by omega naught L. Why? Because at resonance condition we got omega naught L equal to 1 by omega naught C. So that implies omega naught C is equal to 1 by omega naught L from this basic, okay, right? So omega naught RC is also same as R by omega naught L. So this is the quality factor Q, omega naught by bandwidth. Quality factor Q equals to omega naught by bandwidth. Now, for example, if Q is very high, that means if it is greater than or equal to 10, okay, what we can do is this lower half power frequency omega 1 will be approximately equal to omega naught minus bandwidth by 2. And similarly, omega 2, upper half power frequency omega 2 will be our resonant frequency plus half of the bandwidth. Half of the bandwidth. Its meaning is the curve is, observe here. I will tell you. If the curve is more symmetrical, that will be valid. It is something like this. We have a curve like this, right? Now this is exactly at a resonance condition. Value is maximum. For series case, I am explaining you, and this is omega naught. From this context, what does it mean? Your omega 1 will be exactly this value minus bandwidth by 2. For example, if this is the maximum value, Im by root 2, somewhere you will get here, maximum value by root 2, Im by root 2 value. Now we will extend this on the frequency axis omega. This is omega 1, and we will extend this exactly here, and this is omega 2. As the graph is more, it is having more sharpness. Now this omega 1 to omega 2 is our bandwidth, and the distance between omega 1 and omega naught is almost same as the distance between omega naught and omega 2. Then only it is exactly, if you want omega 1, right, exactly, for example, if bandwidth is 10, let me assume bandwidth is 10. To get omega 1, what we can do? Omega naught minus 10 by 2. If I want omega 2, what I can do? Omega naught plus 10 by 2. That is what the meaning. For example, if you got a graph something like this, if you got a current waveform something like this with respect to the frequency, and this is the current, and this is the maximum value, no doubt, Im by root 2 somewhere we got here. Now exactly at the maximum value, this is the resonant frequency, but at half power frequencies, observe, if it is extended on the x-axis, this is omega 1. If the curve is something like this, it is not symmetrical, but omega 2 is here. Now at this case, can you say the distance between omega 1 and omega naught and omega naught to omega 2 is not equal? Is not equal for this graph, observe. So that is the reason why if the quality factor is very high, greater than or equal to 10, our bandwidth omega 1 will be exactly equals to omega naught minus bandwidth by 2. Clear? That is what the meaning. But in this graph, the distance from omega 1 to omega naught is not same as omega naught to omega 2. But the entire distance between omega 1 and omega 2 is bandwidth only. This is bandwidth only. Yeah. So let me do a small problem on the resonance frequency, quality factor, and bandwidth, and current at resonance. Right? So R is given as 5 kilo ohm, L 3 millihenry, C 6 microfarad, and the current is 20 cos 40. If you observe its mathematical form, I of t equals to some Im cos of omega t, right? Now what about resonant frequency? F naught equal to 1 by root LC. I repeat again, while writing or expressing the units 3 millihenry, please don't forget to substitute 3 into 10 power minus 3 Henry. This is where we are committing the mistake, most of the students. Similarly, 6 microfarad, please don't forget to write it as 6 into 10 power minus 6 farad while doing the calculation in the calculator. Then only you will get the correct answer. If you are in a hurry and if you forget this milli and micro, you will get the wrong answer, right? Yeah. Now 7453.5 radians per second. If I want f naught, it is equal to 1 by 2 pi root LC. And if I express it in kilohertz, we will get as 1.185 kilohertz. 1.185 kilohertz. What about quality factor? Quality factor Q equals to R by omega naught into L. What is R? So here, and this is wrong. Quality factor Q equals to the mistake committed, and it is omega naught L by R only. Okay, so that is now the inverse of this one. 1 divided by 223.6 we will get. That is the quality factor, right? Anywhere written R by omega naught L, quality factor Q equals to. Yeah, in parallel circuit, this is correct only, right? Now, it's not like this. Sorry, this is R by omega naught L only. That is for another circuit, R by omega naught L, and this is correct only. The value of Q is very high, right? And if you want this, you can refer Charles Alexander. If you have any doubt, you can see refer to the electrical circuit fundamentals of electrical circuits by Charles Alexander. R by omega naught L. Now the bandwidth B is given by omega naught by Q. So 33.33 radians per second. Now what about at resonance? V equal to Im into R. Im is 20, R is 5000, and it will be 100 kV, right? Now to calculate omega 1 and omega 2, right? And and also the power dissipated at omega equals to omega naught. If you observe, we got a value of Q which is very high. Then obviously the omega 1 will be equal to omega naught minus bandwidth by 2. Omega naught already we have found out, minus bandwidth by 2 radians per second. Similarly, omega 2 will be omega naught plus bandwidth by 2, right? This also we will get 7470.16 radians per second. Now whatever the power of I square R, how the power dissipated at resonant frequency of I square R, half into Im square, 20 square into R, that is around 1000 kilowatt we are getting. The values we are getting are very high, right? Actually might be all this is because of the taken values of RLC. Okay, right? So this is all about the series resonance. Sorry, parallel resonance, right? These are all the important basics. Just simply make the imaginary part of the given circuit admittance. They are parallel equal to 0. Then you will get the answer, right?